I'm doing lesson 1 for proof. So this is all of OCR A MEI Maths lessons. So I'm according to the specification, this is the first lesson, so let's go. So for this, we need to first know what is a proof. So in simple terms, a proof is like a step-by-step explanation that shows why something in math is definitely true. So for all these questions that you are doing for proof, you need to show all your working or you won't get the marks. So the way a proof normally works, you start off with the facts you already know, so the basic rules. So for example, if you have something like I'll cover this after as well, but if you have something like if n is even, right, how would you write it? So if you're saying n is even, you can write it as n is going to be equal to 2k. Okay, so that's saying that where k is an integer, n can be any even number. And so that's what it means by starting with the facts that you already know. Then you can use the logic to build up your argument, and showing clearly at the end you can prove it happens for every single n, for example. Okay, so there are 3 proofs that you need to know. So in these videos I'm going to be using a smiley green man or a smiley red man. Okay, so the smiley green man, I mean, it's pretty easy, it's self-explanatory, but I'm still going to go through it. The red man means it's pretty hard. It's probably one of the hardest topics that I think in the whole OCR MEI or A specification. So our 3 proofs are proof by deduction, proof by exhaustion, and proof by contradiction. I think in GCSE you would have done both proof by deduction and proof by exhaustion, but they wouldn't have named it like that. Proof by contradiction would be completely new to you. So what is proof by deduction? It's a way of showing something is true by stating from known facts or given rules. So in our last page I said you start off with facts, and that is what proof by deduction exactly does. And it uses logical steps to reach a conclusion. You can think of it as a puzzle by using clues, each time getting closer to a full picture. So let's say, for example, they gave you this in the question. If n is even, then n squared is even, right? So how do we do this? So we want to prove this is true, right? So you want to start off with what you're given. So you're given that n is an even number. So that means that n equals 2k. Okay? If you said n is odd, right? Then think about it. If n equals 2k is even, so let's think of it as a number line. 2, 3, and 4, right? If n is even, that means that, okay, so let's put k equals 1, right? If k equals 1, that means n is 2, okay? That means that nk plus 1, which is 3, is odd. So instead of writing n equals 2k for even, you can write n is equal to 2k plus 1. Okay, so this is only if odd, right? If it's an odd, always use n equals 2k plus 1 or 2k minus 1. Both work. Okay, so for this example, we're not doing that, so I'm just going to rub this thing off. Okay, so use the definition of even, so n equals 2k. Now work from that. So if you're saying that n squared, you know that n equals 2k, so you just sub it in. So n squared equals 2k squared, which is equal to 4k squared, which gives us 2k squared. Okay. So the reason why I actually took out the 2 is to show it is actually even, because any multiple of 2 is even. So this works. Conclusion: n squared is divisible by 2, so n squared is even. Okay. So that's how we deduced it. That's what it's called proof by deduction. We do deduce something. The next type of proof is proof by contradiction. So it's a method of proving something by checking every possible case one by one and showing that it works in all of them. So this is pretty easy. So if the example is prove if a number n is a whole number less than 4, then n squared is less than 20. Okay, so if we think about it, it says a whole number less than 4. That means that the possible values are 0, 1, 2, 3. And now you just want to check that for each number 0, 1, 2, 3, it satisfies n squared is less than 20. So if we put in n equals 0, 0 squared is 0, which is less than 20. 1 squared is 1, which is less than 20. 2 squared is 4, which is less than 20. 3 squared is 9, which is less than 20. So all cases work are true, right? With if it said it's whole number less than 4, that means it is true for all n is less than 4. Okay, so it's a pretty easy one. Now our next proof is probably the hardest proof for single maths. So you've got proof by contradiction is a method of proving something is true by assuming the opposite of what you want to prove, showing that this assumption leads to a logical contradiction, concluding that your original statement must be true. So at the start, you want to assume the opposite of what you want to prove. So the slide after this will show an example, so I'll just go to that actually. So this is probably the most simplest proof, it's the most well-known proof. It's saying prove root 2 is not a rational number. So what does rational number mean? It can't be written as a fraction, right? So a rational number means it can be written as a fraction, irrational means it can't be written as a fraction. Example of rational is 1 out of 2, right? Example of irrational is pi. So proof by contradiction, assume the opposite. So that's our first step, okay? Our first step is assume the opposite of what you're trying to prove. So let's suppose root 2 is rational, right? So wherever we see is not, just change it to is, okay? So if root 2 is rational, I said that if it is rational, then it can be written as a fraction, right? So you can write, okay, root 2 equals a over b, where a and b are whole numbers with no common factors. So that means that they're in simplest form. So now we've done that. Now this is a bit of a memorization thing here. So you just want to say, okay, 2 equals a squared over b squared. A squared equals 2b squared. Okay, so that means that a squared is even. That means that must mean a must be even as well. So a equals 2k. Okay. Then a squared equals 4k squared. Okay, so what we did, we just squared both sides. So that means that 2b squared equals 4k squared. B squared equals 2k squared. So b must also be even. Okay, that means that if a is even and b is even, they have a common factor of 2. And that is a contradiction, as we said in our proof. Root 2 equals a over b, where a and b are whole numbers with no common factors. Okay, so that's the whole layout on this. Here's one harder one. Proof of there is infinitely many prime numbers. So you want to assume the opposite. Because it says there is infinitely many prime numbers, you want to say there are only a finite number of prime numbers. Okay, so then you say, okay, let the prime numbers be p1, p2, p3, all the way up to pn. Now you want to consider n, which is equal to all these prime numbers multiplied together plus 1. N is greater than all the known prime numbers and is not divisible by any of them, okay? Right, because if you're doing all of these prime numbers plus 1, n has to be greater than all of these prime numbers itself. So that means that n is either prime itself, which contradicts the list being complete because n is not actually in our list, or n has a prime factor that's not in a list, again a contradiction. As we said, a prime number is something that can't be divisible by something else, so the assumption is false. So that's all the proofs that we've been through, and